Deep in space, a hole 3 billion times more massive than our star is pulling galaxies toward it, not gently, violently. This thing tears apart everything within billions of miles, twists time until seconds become centuries, and bends light into spirals that should not exist. We are about to journey past its edge, into the disk where matter burns hotter than anything in the universe, through jets shooting faster than you can imagine, and toward the center where reality itself breaks. If you are ready to see the most extreme object in existence, hit that like button and subscribe. What comes next will change how you see the cosmos. Let's begin. Something is wrong with the hole at the center of galaxy Messier 87. Astronomers have studied hundreds of these objects, mapped their behavior, predicted their size. They thought they understood the rules. Then they measured this one. The numbers came back impossible. Most cosmic holes sit quietly, consuming nearby gas and dust. They pull material in slowly, over millions of years, growing at a steady pace. Scientists can calculate their mass by watching how stars orbit around them. The math works. The predictions match reality. Everything follows the pattern. Messier 87 breaks that pattern completely. This hole weighs 6.5 billion times more than our home star. To picture that scale, imagine our entire stellar neighborhood, every bit of burning gas and nuclear fire, multiplied by billions. Now crush all of that into a region smaller than our planetary system. The density becomes so extreme that space itself cannot hold its normal shape anymore. Here is where things get stranger. The hole sits 53 million light-years away, in a galaxy cluster called Virgo. Astronomers pointed their telescopes at it, expecting another typical measurement. What they found instead was a monster actively feeding. Material spirals into it at millions of miles per hour. As that material accelerates, friction heats it to temperatures no normal matter can reach. The disk glows brighter than 1 trillion stars combined. But brightness alone does not make this hole unique. The real shock came when scientists measured how fast the hole spins. Most of these objects rotate, dragging space-time around them like a whirlpool drags water. Rotation creates energy. Energy powers jets. These jets shoot outward from the poles, carrying matter and radiation across distances that dwarf galaxies. Messier 87's jets stretch 15,000 light-years into space. Picture a beam of superheated particles, moving at 99% the speed of light, extending farther than the width of our entire galactic home. The energy required to maintain those jets exceeds the total output of billions of stars burning for billions of years. Where does that power come from? The spin, the rotation rate approaches the theoretical maximum, the fastest anything with mass can possibly turn. Physicists calculated that limit decades ago. They assumed no real object would ever reach it. Messier 87 came close enough to prove them wrong. The discovery raised immediate questions. How did this hole grow so massive? Why does it spin so fast? What happens to the rules when an object pushes right up against cosmic speed limits? Teams of researchers began studying the surrounding galaxy for clues. They found evidence of ancient collisions, galaxies merging together, combining their central holes into something larger. Each merger adds mass. Each merger adds spin. Over billions of years, collision after collision, the hole at the center grew into the beast we see today. Yet, even that explanation falls short. Computer simulations show that mergers alone cannot produce something this extreme. The math suggests there must be another mechanism, some additional process feeding the hole faster than collisions can account for. Scientists have proposed theories involving dark matter, exotic particles, even the fabric of space itself, funneling energy inward. None of these ideas have been confirmed. The mystery remains open. What we do know is this. Messier 87 hosts the first cosmic hole ever photographed directly. In 2019, a network of telescopes spanning Earth captured an image of its shadow. That photograph showed a dark circle surrounded by a glowing ring of light. The ring matched predictions perfectly. The size, however, shocked everyone. The shadow measures 25 billion miles across. That distance is larger than our entire planetary orbit, larger than the space between our star and the farthest ice worlds. The scale defies comprehension. Yet this is just the beginning. The size of that shadow connects directly to what happens at the edge, where gravity becomes so intense that escape turns impossible. What lies at that boundary is even more terrifying. Scientists measure cosmic holes using a boundary called the event horizon. This is the point where gravity wins permanently. Anything crossing that line never comes back. Light, matter, energy, information itself vanishes beyond recovery. The size of this boundary depends entirely on mass. More mass means a larger horizon. For Messier 87, that horizon stretches 19 billion miles in diameter. Imagine flying toward it in the fastest spacecraft humans have built. Voyager 1 travels at 38,000 miles per hour. At that speed, crossing the distance from one side of the horizon to the other would take 57,000 years. The scale makes planets look like dust specks. It makes our home star look tiny. This is not a hole. This is a region of destroyed space large enough to swallow entire stellar systems. The mass required to create such a boundary exceeds the total weight of several 100 million stars. Here is the problem. Galaxies like Messier 87 formed relatively recently in cosmic history. The universe is 13.8 billion years old. This galaxy appears in telescope images as it looked 53 million years ago, meaning we see it in a fairly modern state. Computer models show that holes grow by consuming matter over time. The more they eat, the bigger they get. The math does not work out. Even if this hole started forming immediately after the galaxy appeared, even if it consumed matter at the maximum possible rate, it should not have grown this large. The numbers suggest it would need billions of years longer. Yet here it is, fully formed, spinning near the cosmic limit, dominating its galaxy with gravitational force strong enough to hold thousands of star clusters in orbit. Astronomers call this the supermassive black hole growth problem. The issue gets worse when you zoom out. Messier 87 is large, truly massive by any standard. However, it is far from the largest cosmic hole ever discovered. In a galaxy called TON 618, a hole weighing 66 billion times the mass of our home star lurks at the center. That object makes Messier 87 look small by comparison. Its event horizon would stretch from one end of our planetary system to the other and back again. How can something that massive exist at all? Scientists have proposed several explanations. Maybe these holes formed through direct collapse, where massive gas clouds in the early universe imploded without forming stars first. Maybe they grew through repeated mergers, combining dozens or hundreds of smaller holes into giants. Maybe the laws of physics operated differently in the ancient cosmos, allowing faster growth than current models predict. None of these theories fully explains what we observe. The scale becomes even harder to grasp when you consider density. Despite weighing billions of times more than stars, the average density inside the event horizon is surprisingly low. For the largest holes, density drops below that of water. You could theoretically cross the horizon without immediately noticing anything wrong. The force pulling you inward would increase gradually, smoothly, until eventually the difference between your head and feet becomes too extreme. That difference is called tidal force, and it will matter very soon. For now, focus on the boundary itself. The event horizon is not a physical surface. Nothing solid exists there. It is simply the mathematical point where escape velocity equals the speed of light. Below that point, you would need to travel faster than light to get out. Physics forbids faster than light travel. Therefore, escape becomes impossible. The size of that impossibility zone, 19 billion miles across, represents the scale at which our understanding starts breaking down. Telescopes cannot see past the horizon. Equations cannot describe what happens inside. Even the concept of inside loses meaning when space curves back on itself so severely that direction stops making sense. Scientists have built their best models, run their most sophisticated simulations, tested every mathematical tool available. The answer keeps coming back the same. Beyond the horizon, we simply do not know. What we can measure is how matter behaves just outside that boundary, in the final moments before it vanishes forever. Those measurements revealed something nobody expected. The region right outside the event horizon is the strangest place in the known universe. Radio waves changed everything. For decades, astronomers studied space using visible light, the same wavelengths your eyes detect. Stars shine brightly in visible light. Galaxies glow. Planets reflect light from their parent stars. The technique worked well for mapping ordinary objects. Cosmic holes emit no visible light. They are perfectly dark. They swallow photons. Detecting them directly seemed impossible. Then scientists realized something crucial. Even though the hole itself stays invisible, the material falling toward it radiates energy. That material heats up as it accelerates. Hot matter produces light across the entire electromagnetic spectrum, from radio waves through visible light to gamma rays. By studying those emissions, researchers could map what they could not see directly. The breakthrough came in the 1960s. Astronomers detected mysterious radio sources scattered across the sky. These sources appeared as single points, brighter than entire galaxies, yet smaller than individual stars. The intensity made no sense. Normal stars cannot produce that much radio energy. Neither can gas clouds or planetary nebulae. Whatever created these signals had to be something entirely different. Scientists named them quasars, short for quasi-stellar radio sources. Decades of observation revealed the truth. Quasars are cosmic holes actively feeding. The radio waves come from jets, those enormous beams of particles shooting outward at nearly light speed. As those particles interact with magnetic fields, they spiral and radiate. The radiation travels across space for billions of years before reaching our telescopes. Messier 87 became one of the first nearby galaxies where scientists confirmed a connection between jets and a central hole. The galaxy sits close enough that telescopes can resolve details invisible in more distant objects. Researchers watched the jets change over time, brightening and dimming, twisting and pulsing. They measured the speed of material moving through those jets. The velocities approached 99.5% the speed of light. Nothing except a rotating cosmic hole could accelerate matter to those speeds. Still, confirmation required more evidence. Teams of astronomers turned to a different technique: measuring stellar orbits. Stars near the galaxy center move faster than stars farther out. By tracking those motions over years, scientists can calculate how much mass sits at the center, pulling everything inward. The calculations for Messier 87 showed a concentrated mass point weighing billions of times more than our home star. The only object that dents is a cosmic hole. Yet even with orbital data and jet observations, skeptics remained. They argued that maybe the mass was distributed differently, spread across multiple objects rather than concentrated in one point. Maybe the jets came from some exotic process nobody had discovered yet. The evidence was strong but not conclusive. Everything changed in 2019. A collaboration of 8 radio telescopes spread across Earth simultaneously observed Messier 87. These telescopes worked together as a single instrument, creating an effective lens the size of the planet itself. The technique is called very long baseline interferometry. It allows astronomers to achieve resolution thousands of times, sharper than any individual telescope. The target was the shadow, the dark region created when the hole blocks light from the glowing material behind it. For 5 nights, telescopes in Hawaii, Arizona, Spain, Chile, and Antarctica collected data. Each location recorded petabytes of information, so much that hard drives had to be physically shipped to processing centers because transmitting the data electronically would take too long. Supercomputers spent months combining the signals, correcting for Earth's rotation, accounting for atmospheric interference, calibrating each instrument. The final image appeared in April 2019. It showed exactly what theory predicted: a dark circle surrounded by a bright asymmetric ring. The circle was the shadow. The ring was the accretion disk, matter spiraling inward at incredible speed. One side of the ring glowed brighter because the material there moved toward Earth, boosting the light through a process called relativistic beaming. The image confirmed beyond doubt that cosmic holes exist. More importantly, it confirmed that Einstein's equations work even under the most extreme conditions. The size, shape, and brightness of the shadow matched predictions made using general relativity. A century after Einstein published his theory, this photograph proved he was right about how gravity warps space. But the image also revealed something unexpected about the hole's rotation, something that makes the physics even more extreme. Gravity is not a force pulling objects together. Gravity is the curvature of space itself. Mass bends space, the way a weight bends a trampoline. Objects moving through that bent space follow curved paths. We experience those curves as gravitational attraction. Around a cosmic hole, space curves beyond recognition. Imagine space-time as a fabric stretched flat in all directions. Now place a 6 billion solar mass object at the center. The fabric does not just dip slightly. It plunges downward in a steep well, warping so severely that lines which should run parallel start converging. Light beams traveling near the hole bend inward, following the curves. The bending becomes so extreme that light can orbit the hole like a planet orbits a star. This occurs at a specific distance called the photon sphere. For Messier 87, that sphere sits about 28 billion miles from the center. Any light arriving at exactly that distance will circle forever, trapped in an endless loop. Photons coming from inside the photon sphere spiral inward and cross the horizon. Photons outside can escape to space. The existence of the photon sphere creates the shadow we see in photographs. When light from the accretion disk travels toward us, some of it passes near the hole. That light bends around the curvature, following the warped space-time. If it bends too much, it falls into the photon sphere and disappears. The region where this happens appears dark because no light escapes from it. The shadow is larger than the event horizon itself, about 2.5 times the horizon diameter. Measuring that shadow size lets scientists test whether Einstein's equations accurately describe reality. So far, they do. The shadow dimensions match predictions within measurement error, but predictions also tell us something even stranger happens when the hole rotates. Rotation drags space-time along with it, like stirring honey with a spoon. The honey near the spoon moves faster than honey farther away. Space behaves the same way around a spinning hole. Physicists call this frame dragging. Close to the horizon, frame dragging becomes so strong that nothing can stay still. Even if you fired rocket engines at maximum thrust, trying to hover in place, the rotation of the hole would drag you along. You would spin whether you wanted to or not. The region where this happens is called the ergosphere. It sits just outside the event horizon, extending outward in a shape that bulges at the equator. Inside the ergosphere, space-time itself rotates faster than light. That sentence sounds impossible. Nothing can move faster than light, according to physics. However, the rule applies to objects moving through space, not to space itself. Space can do whatever it wants. It can expand, contract, twist, or rotate at any speed. Objects inside that rotating space get carried along like leaves in a whirlpool. The implications are profound. In theory, you could enter the ergosphere, steal energy from the hole's rotation, and escape back out. The process would slow the hole's spin slightly, while giving you an enormous energy boost. This is called the Penrose process. named after physicist Roger Penrose, who discovered it mathematically in 1969. Nobody has figured out how to actually do this. The engineering challenges are absurd. You would need to build a device capable of operating in an environment where tidal forces and radiation would vaporize any known material. You would need to navigate space-time so warped that directions lose meaning. You would need to extract energy faster than the hole swallows your equipment. Still, the math says it works. That same math also reveals what happens to time near the horizon. Clocks moving through curved space-time tick at different rates depending on how strong the curvature is. Near a cosmic hole, time slows dramatically. An observer far away, watching someone fall toward the horizon, would see that person move slower and slower, asymptotically approaching the boundary without ever quite reaching it. The person falling, meanwhile, would experience time normally. From their perspective, they would cross the horizon in finite time, maybe a few seconds or minutes depending on the hole's mass. They would notice nothing special at the boundary itself. The event horizon is not a physical barrier. It is simply a point of no return. But the time distortion creates a paradox that has bothered physicists for decades, and it gets worse the closer you look. Light always moves at the same speed through empty space, 300 million meters per second. This is a universal constant, the foundation of relativity. Nothing moves faster. Nothing can make light speed up or slow down. Except, space-time curvature changes the rules. Near the event horizon, space bends so steeply that light trying to escape has to climb an infinite hill. Imagine running up a mountain that gets steeper with every step. Eventually, the slope becomes vertical. Then it curves backward. Light faces the same problem. It moves at constant speed through space, but the space itself curves back toward the hole. The result is that light trying to escape gets redshifted. Redshift means the wavelength stretches. Visible light shifts toward the red end of the spectrum. Red light shifts into infrared. Infrared shifts into radio waves. The effect becomes more extreme the closer you get to the horizon. Light emitted just above the boundary stretches to infinite wavelength, becoming effectively invisible. This is called gravitational redshift, and it has been measured around Messier 87. Astronomers observed light from hot gas orbiting close to the hole. That light appeared dimmer and redder than it should based on the gas temperature. The shift matched predictions from relativity equations. The measurements confirmed that space-time near the horizon warps exactly as Einstein described. But redshift is just one of several strange effects. Light traveling near the hole also bends in unexpected ways. A photon passing close to the event horizon curves sharply inward, following the space-time curvature. If it comes too close, it spirals into the photon sphere and orbits forever. If it stays slightly farther out, it bends around the hole and shoots off in a different direction. This bending creates something called gravitational lensing. A background object directly behind the hole appears as a ring around it. Light from that object travels along multiple curved paths, all converging at the observer's position. The hole acts like a lens, focusing light even though it emits none itself. Astronomers use lensing to study cosmic holes too distant to resolve directly. The distorted images reveal the mass and location of the hole doing the lensing. Around Messier 87, lensing creates multiple images of the accretion disk. Light from the far side of the disk curves around both sides of the hole, reaching our telescopes from different angles. This makes the disk appear as a complete ring, even though we are viewing it from an angle. Without lensing, we would see an ellipse, not a circle. The lensing fills in the gaps, bending light around the edges to create the symmetric shape visible in photographs. The brightness distribution also results from lensing effects. One side of the ring glows brighter because the disk rotates. Material on the approaching side moves toward us at a significant fraction of light speed. Relativity tells us that light from an approaching source gets blue shifted and intensified. The opposite side moves away, causing redshift and dimming. This creates the asymmetry visible in images. Measuring that asymmetry reveals how fast the hole spins. Faster rotation means stronger frame dragging, which affects how close material can orbit before falling in. The closest stable orbit moves inward as spin increases. By finding where the bright inner edge of the disk sits, scientists calculate the rotation rate. For Messier 87, the edge location indicates a spin near the maximum possible value. Maximum spin means the hole rotates once every few hours, despite weighing billions of times more than a star. The rotation creates enormous angular momentum, a quantity that measures how hard something is to stop spinning. Conservation laws say angular momentum cannot disappear. It can only transfer to something else. When material falls into the hole, it carries angular momentum inward. That momentum has to go somewhere. Most of it gets absorbed, increasing the hole's spin. Some gets ejected through the jets. The jets form when magnetic fields threading through the accretion disk get twisted by rotation. The twisting creates tension, like winding up a rubber band. Eventually, the fields snap and release their energy as directed beams of particles. Those particles carry momentum away from the hole, preventing it from spinning faster than the theoretical maximum. The balance between infalling and ejected momentum keeps the spin stable. But stability is relative. The hole still spins fast enough to create regions where the normal rules of cause and effect start to fail. Clocks measure time by counting regular intervals. A pendulum swings, a quartz crystal vibrates. An atom emits radiation at a specific frequency. Whatever the mechanism, clocks provide a way to mark the passage of moments. Near a cosmic hole, different clocks tick at different rates. This effect is called gravitational time dilation. It happens because time and space are connected. When space curves, time curves with it. An observer deep in a gravitational well experiences time passing slower than an observer far away. Both observers think their own clock is running normally. They are both right from their own perspective. The mathematics come from general relativity. Einstein showed that the passage of time depends on the strength of the gravitational field. Stronger gravity means slower time. Near Messier 87's event horizon, gravity becomes so intense that time nearly stops from the perspective of a distant observer. A clock held just above the boundary would tick once per hour, compared to a clock sitting in empty space far from any mass. This is not theory. It has been measured. Satellites orbiting Earth experience weaker gravity than objects on the surface. Their onboard clocks tick slightly faster, gaining about 38 microseconds per day compared to ground clocks. GPS systems must account for this difference, or their position calculations would drift by miles. The same physics applies near cosmic holes, just vastly amplified. Imagine watching someone fall toward the horizon. From your safe position far away, you would see them slow down as they descended. Their movements would become sluggish. Their clock would tick slower and slower. Light from their body would redshift, turning dimmer and redder. Eventually, they would appear frozen just above the horizon, their light stretched to infinite wavelength, effectively vanishing from view. The person falling would experience something completely different. From their perspective, time passes normally. They feel no slowdown. Their clock ticks at its usual rate. They cross the horizon in seconds or minutes, depending on the hole's size. Nothing special happens at the boundary itself. No barrier blocks their path. They simply pass through and continue falling toward the center. This creates a paradox. Does the person cross the horizon or not? From outside, they never cross. From their own frame, they do cross. Both descriptions are correct within their respective reference frames. There is no universal now that both observers share. Time itself splits into incompatible perspectives. Physicists spent decades trying to resolve this. The answer is that space-time near a horizon cannot be described using a single coordinate system. you need different mathematical maps for different regions. An observer far away uses one set of coordinates. An infalling observer uses another. The two systems overlap in some regions, but diverge near the boundary. Neither is more correct than the other. They simply describe different viewpoints. The time dilation also affects the accretion disk. Material orbiting close to the hole experiences stronger gravity than material farther out. Inner regions have their time slowed more than outer regions. This creates a gradient where different parts of the disk age at different rates. Gas that completes one orbit near the horizon might experience a few minutes, while gas in the outer disk experiences hours. The difference matters for understanding how the disk evolves. Matter spiraling inward loses energy through friction and radiation. That energy loss causes the orbit to decay, making the material drift closer to the hole over time. The rate of drift depends on how much energy gets radiated per unit time. Time dilation complicates the calculation because different parts of the disk radiate at different effective rates. Computer simulations account for these effects by solving Einstein's equations numerically. The simulations model how particles move through curved spacetime, how magnetic fields evolve, how radiation transports energy from one region to another. They reproduce the observed features of the disk: the bright inner edge, the temperature distribution, the emission spectrum. The match between simulation and observation confirms that time dilation is real and measurable. Another consequence involves communication. If you tried sending radio signals from just above the horizon to a receiver far away, those signals would arrive delayed and redshifted. A message transmitted once per second from your perspective would arrive once per hour from the receiver's perspective. The frequency would drop from radio waves to extremely low-frequency waves. Eventually, if you hovered close enough, the signals would stretch to wavelengths larger than the observable universe. Communication would become impossible. This poses challenges for any hypothetical mission to study a cosmic hole up close. Probe signals would take longer and longer to reach home as the probe descended. Controllers watching from a safe distance would see the probe's data slow to a trickle, then stop entirely, even though from the probe's perspective, everything continued normally until it hit the singularity. The singularity is where time dilation becomes infinite, and the mathematics break down completely. Gas falling toward the horizon does not plunge straight in. It carries angular momentum, the same property that keeps planets orbiting stars instead of crashing into them. That momentum forces the gas into a disk shape, circling the hole like water spiraling down a drain. The disk is called an accretion disk, and it becomes the hottest place in the universe. Material in the disk moves at a significant fraction of light speed. Inner regions orbit faster than outer regions, creating shear between layers. Gas molecules rub against each other, generating friction. That friction converts orbital energy into heat. Temperatures climb to billions of degrees, hot enough to strip electrons from atoms, breaking matter down into a plasma of bare nuclei and free electrons. At these temperatures, matter radiates across the entire electromagnetic spectrum. The inner disk glows brightest in X-rays, high-energy photons created when electrons spiral around magnetic field lines. The outer disk emits visible and ultraviolet light. The outermost edges radiate infrared and radio waves. Telescopes tuned to different wavelengths see different parts of the structure, each revealing unique information about the disk's properties. Messier 87's disk outshines its entire galaxy. The galaxy contains hundreds of billions of stars. Each star produces light through nuclear fusion, burning hydrogen into helium and releasing energy. Add up all that stellar output, and it pales compared to the disk. A single cosmic hole actively feeding generates more radiation than billions of stars combined. This is possible because gravity is more efficient than fusion at converting mass to energy. Fusion turns about 0.7% of mass into energy. Accretion can reach 40% efficiency around a rapidly spinning hole. The process works through frame dragging. As the hole spins, it drags space-time around with it. Material in the disk gets caught in that rotating space, orbiting closer to the horizon than would be possible around a non-rotating hole. The closer orbit means stronger gravity, higher speeds, more friction, and therefore more heat. The heat creates pressure that pushes outward, balancing gravity. Without pressure, the disk would collapse into the hole immediately. The balance between gravity pulling inward and pressure pushing outward maintains the disk structure. This is the same balance that prevents stars from collapsing, just operating under far more extreme conditions. When the balance shifts, the disk becomes unstable. Instabilities create bright flares. Observations show that the disk's brightness varies over time, sometimes changing by factors of 2 or 3 within days or weeks. These flares indicate that clumps of material occasionally break free from stable orbits and plunge toward the horizon. As they fall, they heat up further, releasing a burst of radiation before disappearing forever. The disk also contains powerful magnetic fields. These fields form when the electrically charged plasma moves through space. Moving charges create currents. Currents create magnetic fields. The fields loop and twist through the disk, sometimes becoming tangled into structures that store enormous energy. When those structures reconnect, they release the stored energy explosively, accelerating particles to extreme velocities. The accelerated particles form the jets. Magnetic field lines near the poles act like railway tracks, guiding particles away from the disk at speeds approaching light. The particles spiral along the field lines, radiating as they go. This radiation is what makes the jets visible across millions of light years. The jet from Messier 87 extends farther than the width of our entire galactic home. Measuring the jet properties reveals information about the disk. The jet's brightness depends on how much material the disk feeds into it. The jet's speed depends on how strong the magnetic fields are. The jet's direction depends on the hole's spin axis. By observing jets from multiple angles and at different wavelengths, astronomers piece together a picture of conditions in the disk itself. One crucial measurement involves the disk's inner edge. Theory predicts that stable circular orbits cannot exist below a certain distance from the horizon. That distance depends on the hole's spin. For a non-rotating hole, the innermost stable orbit sits 6 times farther from the center than the horizon radius. For a maximally spinning hole, it drops to just above the horizon itself. Finding where the bright inner edge sits tells scientists how fast the hole spins. For Messier 87, the edge sits very close to the horizon, indicating near maximal spin. The rotation rate approaches the theoretical limit where frame dragging becomes so extreme that space itself rotates at light speed. At that limit, further acceleration becomes impossible. Adding more spin would require exceeding light speed, which physics forbids. The disk cannot survive forever. Material constantly drains into the hole, and eventually, the supply will run out, leaving only the jets to mark where something once fed. 2 beams of particles erupt from the poles of Messier 87. They shoot outward in opposite directions, perpendicular to the accretion disk. These are the jets, and they stretch 15,000 light-years into space. That distance exceeds the diameter of our galactic home. The jets move at 99% the speed of light. At that velocity, particles experience time dilation so extreme that their onboard clocks run 1,000 times slower than clocks at rest. From the particle's perspective, the 15,000 light-year journey takes just 15 years. From our perspective, watching from outside, it takes 15,000 years. How do jets form? The mechanism involves magnetic fields threading through the disk. As the disk rotates, it drags those fields around. The rotation twists the field lines into spiral shapes. Twisted fields store energy like wound-up springs. When enough twist accumulates, the fields become unstable. They snap outward, releasing their stored energy along the path of least resistance. The poles, particles caught in this release get flung away from the hole. Electrons and protons accelerate to extreme velocities within seconds. The acceleration happens so quickly that the particles barely have time to interact with surrounding matter. They shoot through the disk like bullets through air, emerging into the empty space above and below the hole's equator. Once clear of the disk, the jets maintain their shape through magnetic confinement. The field lines act like invisible tubes, keeping particles focused in narrow beams. Without this confinement, the jets would spread out and fade. Instead, they remain collimated across thousands of light years, only gradually widening as they travel. Collimation, this persistent, requires incredibly strong magnetic fields. Measurements suggest field strengths millions of times greater than Earth's magnetic field. These fields dominate the jet physics, controlling how particles move, how they radiate, and how far they can travel before running out of energy. Energy loss happens through synchrotron radiation. When charged particles spiral around magnetic field lines at near light speeds, they radiate electromagnetic energy. The radiation carries away momentum, gradually slowing the particles down. Eventually, they lose enough energy that they fall out of the jet and mix with surrounding intergalactic gas. The distance they travel before this happens depends on how much energy they started with. Particles near the jet core carry more energy than particles at the edges. Core particles can travel thousands of light years. Edge particles might last only hundreds. This creates a structure where the jet has a bright central spine surrounded by a dimmer sheath. Telescopes detect the jets by imaging their synchrotron emission. Radio telescopes excel at this because synchrotron radiation from electrons peaks in the radio spectrum. Observations show the jets flickering and changing brightness over months or years. Sometimes knots of emission appear, bright spots that move along the jet at speeds that seem to exceed light. The apparent faster-than-light motion is an illusion caused by perspective. Imagine a jet aimed almost directly at you but tilted slightly to one side. Material moving toward you at 99% light speed covers most of the distance in the time it takes light to travel the full distance. From your viewpoint, the material appears to jump forward faster than light could travel. The effect is called superluminal motion, and it confirms the jets really do move at speeds very close to light. Where do the jets eventually stop? They plow into the intergalactic medium, gas floating between galaxies. The collision creates shock waves, heating the gas and creating giant lobes of radio emission. These lobes can grow larger than the galaxy itself, spreading across millions of light years. They mark the cumulative impact of jets operating for millions of years. Messier 87 has visible lobes. Images show diffuse radio emission extending far beyond the optical galaxy. The lobes are old, filled with particles that left the hole long ago. They are fading because new particles are not reaching them anymore. The jets have changed direction over geological time, leaving behind these relics of past activity. Directional changes happen when the hole's spin axis wobbles. Any asymmetry in the accretion flow can apply torque to the hole, slowly twisting its rotation axis. Over millions of years, the axis can shift by tens of degrees. The jets follow the axis, sweeping across space like searchlights, carving new paths through the intergalactic gas. The total energy output from jets is staggering. A single jet from a hole like this one can output more power than 10 billion stars. Multiply by 2 for both jets, and the number doubles. This energy pumps into the surrounding environment, affecting galaxy evolution, preventing gas from cooling and forming new stars, shaping the large-scale structure of galaxy clusters. The power comes from the hole's rotation, but there is a limit to how much energy can be extracted before something breaks. Material does not fall straight into the hole, it spirals. Every particle follows a curved path, circling dozens or hundreds of times before finally crossing the event horizon. The spiral tightens gradually, bringing matter closer to the point of no return. This happens because of angular momentum conservation. When gas clouds collapse toward the hole, they carry rotation with them. That rotation comes from the initial motion of the cloud, tiny variations in velocity that become amplified as space shrinks. Just as a figure skater spins faster when pulling their arms inward, collapsing gas rotates faster as it falls. Faster rotation means the gas cannot fall directly inward. Instead, it settles into orbits, circling the hole while gradually losing energy. Energy loss happens through collisions between particles, through radiation, through magnetic interactions. Each energy loss causes the orbit to decay slightly, bringing the particle closer to the horizon. The decay continues for days, weeks, or months depending on initial conditions. Gas starting far from the hole takes longer to spiral in. Gas starting close spirals in quickly. The difference creates a traffic jam effect where material piles up at certain radii, forming dense rings within the accretion disk. These rings are not solid structures. They are concentrations of gas, regions where particle density peaks. Observations reveal multiple rings in some accretion disks, each glowing at a different temperature. The innermost ring glows brightest and hottest because it orbits fastest and experiences the strongest friction. Outer rings are cooler and dimmer. Together, they create a temperature gradient that radiates energy across the electromagnetic spectrum. The spiral pattern also affects how quickly the hole grows. A hole gains mass by consuming the material that crosses its event horizon. The rate of consumption depends on how much material reaches the inner disk. If gas spirals in slowly, the hole grows slowly. If gas spirals in rapidly, the hole grows rapidly. Messier 87 grows relatively slowly today. Observations suggest it consumes roughly 1 Earth mass per day. That sounds like a lot, until you remember the hole weighs 6 billion times more than our home star. At the current consumption rate, it would take trillions of years for the hole to double in size. This indicates the galaxy is not actively feeding its central hole very much right now. The situation was different in the past. Billions of years ago, galaxies contained more gas. Star formation rates were higher. Cosmic holes grew faster because more material was available to feed them. Messier 87 likely gained most of its mass during that era, devouring gas clouds and smaller holes through mergers. Today, the galaxy has settled into a quieter state. Most of the available gas has already been consumed or expelled. What remains spirals inward slowly, maintaining the accretion disk, but not significantly increasing the hole's mass. This quiescent phase will continue until something disrupts the balance, perhaps a future galactic collision that brings fresh gas supplies. The spiral also creates gravitational waves. When massive objects orbit close to each other, they radiate gravitational energy. This energy escapes as ripples in space-time itself, waves that propagate outward at light speed. The waves carry away orbital energy, causing the objects to spiral closer together. For material orbiting a cosmic hole, gravitational wave emission is usually negligible. Individual particles have too little mass to create detectable waves. However, when two cosmic holes orbit each other before merging, gravitational wave emission dominates. The holes spiral together over millions of years, eventually colliding and forming a single, larger hole. Detectors like LIGO have measured these mergers. The observations confirm that gravitational waves exist and propagate exactly as Einstein's equations predict. Each detected merger provides data about hole masses, spins, and orbital parameters. Scientists use this information to test general relativity under extreme conditions and to study how holes form and evolve. Messier 87 itself may have formed through multiple mergers. Computer simulations show that galaxy collisions bring central holes together. The holes sink toward the merged galaxy's center through a process called dynamical friction. Once close enough, they form a binary pair, orbiting each other before finally merging. Each merger adds mass and can add spin. If the merging holes spin in the same direction, the final hole spins faster than either parent. If they spin in opposite directions, angular momentum cancels, producing a slower spinning result. The final spin depends on the details of the merger geometry and the initial spins. For Messier 87, the high spin suggests the holes that merged all rotated in roughly the same direction, aligned with the galaxy's rotation axis. Silence does not exist near a cosmic hole. The accretion disk roars with acoustic energy, pressure waves rippling through the plasma at speeds faster than ordinary sound. These waves carry enormous power, enough to tear apart planets if any existed nearby. The waves form when material in the disk becomes unstable. Regions where gas density varies create pressure differences. High pressure zones push into low pressure zones, creating waves that propagate outward. Normally, these waves dissipate quickly, their energy absorbed by the surrounding medium. Near a cosmic hole, the extreme conditions amplify them instead. Amplification happens through a feedback loop involving magnetic fields. Pressure waves disturb the plasma, causing the magnetic fields threading through it to oscillate. Oscillating fields accelerate particles, which radiate energy. That radiation heats the plasma, increasing pressure and strengthening the waves. The cycle repeats, building wave amplitude until it reaches equilibrium with energy loss mechanisms. The resulting sound waves have frequencies measured in millihertz. That is far below the range of human hearing, which spans 20 Hz to 20 kHz. A millihertz wave has a period of 1,000 seconds, meaning one complete oscillation takes about 16 minutes. Translating such a low frequency to audible sound requires speeding it up by a factor of billions. Despite being inaudible, the waves are incredibly powerful. Calculations show that acoustic power output from the disk can reach 10 to the 40 watts. For comparison, our home star outputs 4 times 10 to the 26 watts. The disk produces 1 trillion times more acoustic power than a star produces total power. That energy pumps into the surrounding gas, preventing it from cooling and collapsing. This process is called acoustic heating. It explains why galaxy clusters, which contain enormous amounts of hot gas, do not cool down and form stars more rapidly. The gas should radiate energy and condense, triggering runaway star formation. Observations show this does not happen. Instead, the gas remains hot and diffuse. Acoustic heating from the central hole provides the energy input needed to balance radiative cooling. Messier 87 sits at the center of the Virgo cluster, where this process operates. Telescopes detect cavities in the surrounding gas, bubble-shaped regions where pressure waves have pushed material aside. The bubbles are enormous, spanning tens of thousands of light years. They form when jets plow through the gas, creating shocks that generate sound waves. Those waves propagate outward, heating the cluster gas. The waves also affect star formation rates. Hot gas does not collapse easily. It has too much thermal energy. Stars require cold, dense gas to form. By keeping cluster gas hot, acoustic heating suppresses star formation across millions of light years. This shapes the evolution of entire galaxy clusters, determining which galaxies grow and which do not. Sound waves carry momentum as well as energy. When a wave encounters an obstacle, it can push that obstacle along. In the disk, waves push particles inward or outward depending on wave direction. Inward traveling waves add to the spiral, accelerating infall. Outward traveling waves can launch material into jets or winds. Winds are streams of gas blown away from the disk by radiation and magnetic pressure. Unlike jets, which are tightly collimated, winds spread out over wide angles. They carry away mass, energy, and angular momentum, affecting how the whole grows over time. Strong winds can limit accretion rates by removing material before it reaches the inner disk. Observations of Messier 87 show evidence for winds. Spectroscopy reveals gas moving outward at speeds of thousands of miles per second. The gas shows signatures of being ionized by intense radiation, confirming it originates near the disk. The mass loss rate through winds approaches the accretion rate, meaning nearly as much gas escapes as falls in. This balance between inflow and outflow regulates hole growth. Without winds, the hole would consume material faster. With too much wind, accretion would stop entirely. The equilibrium point depends on disk properties, magnetic field strength, and radiation intensity. Different holes reach different equilibria, explaining why some grow rapidly while others stay roughly constant in mass. Acoustic waves also generate turbulence. Turbulence is chaotic motion, where flow patterns change unpredictably over time. In the disk, turbulence arises when waves interact with each other, creating eddies and vortices. These structures mix the disk material, transporting angular momentum outward and allowing mass to drift inward. Without turbulence, accretion would be much slower. Smooth, laminar flow preserves angular momentum, keeping material in stable orbits indefinitely. Turbulence breaks that stability, providing a mechanism for viscosity that drains orbital energy. Scientists model turbulence using magnetohydrodynamics, equations that describe how magnetic fields and fluids interact. The models reproduce observed disk properties. They predict temperatures, densities, and emission spectra that match measurements. They explain why disks have inner edges at specific radii. They show how jets form and how winds escape. The success of these models confirms that our understanding of disk physics is largely correct. Yet one mystery remains. Where does the material feeding the disk come from in the first place? When two cosmic holes merge, they create the strongest gravitational waves in the universe. The collision warps spacetime so violently that ripples spread outward at light speed, carrying energy away from the merger site. These ripples travel across billions of light years, stretching and squeezing space as they pass. Gravitational waves are not like electromagnetic waves. Electromagnetic waves oscillate electric and magnetic fields. Gravitational waves oscillate the fabric of spacetime itself. As a wave passes through a region, distances between objects change slightly. Space stretches in one direction and compresses perpendicular to that direction, then reverses. The effect is tiny but measurable. LIGO detected the first gravitational waves in 2015. The signal came from two cosmic holes, each roughly 30 times the mass of our home star, orbiting each other before merging. The waves traveled for over 1 billion years before reaching Earth. When they arrived, they changed the distance between LIGO's mirrors by less than 1,000th the width of a proton. That measurement required the most sensitive instruments ever built. LIGO uses laser interferometry to detect distance changes. A laser beam splits and travels down two perpendicular arms, each several miles long. The beams reflect off mirrors and recombine. If the arm lengths change, the beams interfere differently, creating a measurable signal. Gravitational waves passing through the detector change the arm lengths in a characteristic pattern. The pattern reveals information about the source. Wave frequency tells you how fast the holes orbited before merging. Higher frequency means tighter orbits. Amplitude tells you how massive the holes were and how far away the merger happened. The duration of the signal tells you how long the inspiral lasted. For the 2015 detection, the signal lasted only a fraction of a second. The holes spiraled together rapidly in the final moments, accelerating to significant fractions of light speed before colliding. The merger converted 3 times our home star's mass into gravitational wave energy. That energy radiated away in seconds, making the event one of the most luminous occurrences in the universe. Since then, LIGO and similar detectors have observed dozens of mergers. Each detection adds data about the whole population, their masses, spins, and merger rates. Scientists use this information to reconstruct how holes form. Do they come from collapsing stars? Do they form directly from gas clouds? Do they grow by merging with other holes? The answers are beginning to emerge. Most detected holes have masses between 5 and 50 times that of our home star. These likely formed from massive stars that exhausted their fuel and collapsed. Heavier holes, weighing hundreds or thousands of stellar masses, probably formed through mergers. The heaviest ones, like Messier 87, grew through millions of years of accretion and repeated mergers. Future detectors will observe even larger mergers. The Laser Interferometer space antenna, planned for launch in the 2030s, will detect waves from holes weighing millions or billions of solar masses. These mergers happen when galaxies collide, bringing their central holes together. The final merger produces a gravitational wave signal lasting months or years, detectable across the entire observable universe. Messier 87 might have merged with other holes in the past. Evidence comes from its high spin. Mergers can increase spin if the holes orbit in the same direction before colliding. Multiple mergers over billions of years could spin the hole up to near maximum rotation. Computer simulations support this scenario, showing that repeated mergers naturally produce highly spinning holes. Gravitational waves also affect the hole's environment. As waves pass through the accretion disk, they stretch and compress the gas. This creates turbulence and can trigger bursts of accretion. The bursts produce flares, temporary increases in brightness as extra material spirals into the hole. Observers have seen such flares following galaxy mergers, supporting the connection between mergers and activity. The waves carry away orbital energy. When two holes orbit each other, they radiate gravitational energy continuously. The energy loss causes the orbit to decay. The holes spiral closer together, orbiting faster, radiating more energy. The process accelerates, culminating in a rapid plunge and merger. The final moments release the most energy. Just before merging, the holes orbit each other hundreds of times per second. Each orbit radiates immense power. The peak luminosity exceeds the combined light output of every star in the observable universe. For that brief instant, the merging holes are the brightest gravitational wave sources in existence. After the merger, the remnant hole settles down. It vibrates like a struck bell, ringing with characteristic frequencies determined by its mass and spin. These ring-down oscillations emit gravitational waves for a short time before damping out. The ring-down signal confirms the merger produced a single hole rather than some exotic object. Einstein predicted all of this a century ago. The mathematics works perfectly, but the equations cannot describe what happens at the very center of the hole. April 10th, 2019, scientists released the first image of a cosmic hole's shadow. The photograph showed a dark circle surrounded by a glowing ring, captured by coordinating 8 telescopes across 4 continents. The target was Messier 87, 53 million light-years away. The project was called the Event Horizon Telescope. Traditional telescopes collect light using mirrors or lenses. Resolution depends on telescope size. Larger telescopes see finer details. To image a cosmic hole's shadow requires resolution equivalent to seeing a grapefruit on the lunar surface. No single telescope can achieve this. The solution was to combine multiple telescopes into a virtual instrument the size of Earth. The technique is called Very Long Baseline Interferometry. It works by recording signals at multiple locations and combining them later. Each telescope collects data independently, time-stamping it using atomic clocks. Computers then correlate the signals, searching for patterns that appear at multiple sites. The correlation reveals details smaller than any individual telescope could detect. 8 observatories participated in the observations. Sites included the Atacama Large Millimeter Array in Chile, the James Clerk Maxwell Telescope in Hawaii, the Large Millimeter Telescope in Mexico, the Sub-Millimeter Array in Hawaii, the Sub-Millimeter Telescope in Arizona, the IRAM Telescope in Spain, the South Pole Telescope in Antarctica, and the Atacama Pathfinder Experiment in Chile. Coordination was critical. All telescopes had to observe the same target simultaneously. The observations took place over 5 nights in April 2017. Weather needed to be clear at all sites. Equipment had to function perfectly. Atomic clocks had to maintain synchronization to within nanoseconds. Any failure would ruin the data. Each night generated petabytes of information. Petabytes are millions of gigabytes. The data volume was so large that shipping hard drives physically was faster than transmitting the data over the internet. Drives from the South Pole could only be retrieved months later when Antarctic winter ended. Processing the data took 2 years. Supercomputers correlated signals from different sites, accounting for Earth's rotation, atmospheric effects, and instrumental variations. Multiple independent teams analyzed the data using different algorithms. All teams reached the same conclusion: the shadow was real. The final image appeared as predicted. A dark circle, 25 billion miles across, surrounded by an asymmetric ring. One side of the ring glowed brighter because the disk rotates. Material moving toward Earth appears brighter due to relativistic beaming. Material moving away appears dimmer. The asymmetry matched simulations based on Einstein's equations. The image confirmed several predictions. First, cosmic holes exist. The shadow proved that a region of trapped space-time sits at the galaxy's center. Second, general relativity works. The shadow's size and shape agreed with calculations based on Einstein's theory. Third, the hole spins. The bright region's location indicated rotation near the maximum possible rate. Scientists measured the shadow diameter to calculate the hole's mass. The shadow is larger than the event horizon by a factor of 2.6. Knowing this ratio and measuring the shadow size gives the horizon size. The horizon size depends on mass through a simple equation. Plugging in the numbers yielded a mass of 6.5 billion times our home star's mass. The measurement agreed with earlier estimates based on stellar orbits. This consistency validated both methods. It showed that different observational techniques produce compatible results when measuring the same object. The agreement strengthened confidence in our understanding of these extreme objects. The photograph also revealed the disk's structure. The ring is not uniform. It shows variations in brightness, clumps of emission moving around the hole. These features change over days or weeks as hotspots in the disk orbit and evolve. Tracking these changes provides information about disk dynamics, magnetic field strength, and turbulence levels. Future observations will watch the shadow change over time. The Event Horizon Telescope continues operating, taking new images during annual observation campaigns. Comparing images from different years shows how the disk evolves, how jets vary, and whether the shadow size changes. Long-term monitoring could detect the hole's growth or changes in spin. The success of the project inspired plans for improvements. Adding more telescopes to the array will increase resolution and sensitivity. Observing at shorter wavelengths will sharpen the image further. Space-based telescopes could extend the baseline beyond Earth's diameter, achieving even finer detail. One goal is imaging the hole at our galaxy's center. That hole weighs only 4 million solar masses, much smaller than Messier 87. However, it sits much closer, just 26,000 light-years away. Its angular size is comparable, making it another excellent target. Imaging both holes will reveal how disk properties vary with mass. Another goal is making movies instead of still images. Current observations produce snapshots showing the disk at one moment. Future campaigns could collect enough data to track changes in real time, creating videos of material spiraling into the hole. These movies would provide unprecedented insight into accretion dynamics. The photograph answered old questions, but raised new ones about what exists inside the shadow itself. Weighing a cosmic hole requires watching how objects move around it. Stars orbit the hole, pulled by its gravity. Faster orbits mean stronger gravity. Stronger gravity means more mass. The math is straightforward. Apply Newton's or Einstein's equations to the orbital data and the mass falls out. For Messier 87, the calculation produced a shocking result: 6.5 billion times the mass of our home star. Written out, that is 6,500,000 solar masses. The number is so large that it challenges theories of hole formation. How did something that massive come into existence? Standard models struggle to explain it. One theory says holes form when massive stars collapse. When a star exhausts its nuclear fuel, its core implodes under gravity. If the core is heavy enough, the collapse continues past neutron star density, forming a cosmic hole. These stellar holes weigh 5 to 100 solar masses. Messier 87 weighs 65 million times more than the heaviest stellar hole. Getting from 100 solar masses to billions requires growth mechanisms. Two main options exist: accretion and mergers. Accretion means consuming gas from the surrounding environment. Mergers mean combining with other holes. Both processes take time. The problem is there has not been enough time. Messier 87's galaxy formed roughly 10 billion years ago. The hole would need to grow from stellar mass to billions of solar masses in that time frame. Accretion rates have physical limits. A hole can only consume matter so fast before radiation pressure from the infalling material pushes new material away. This limit is called the Eddington limit. It depends on the hole's mass and the efficiency of converting mass to radiation. For a hole accreting at the Eddington limit, the mass doubles roughly every 50 million years. Starting from 100 solar masses and doubling every 50 million years gives about 100 doublings in 10 billion years. 100 doublings produces a final mass around 10 to the 30 times the initial mass. That calculation works out to approximately 100 billion solar masses. Messier 87 weighs only 6.5 billion, well within what Eddington limited accretion can produce. So what is the problem? The issue is that holes do not accrete at the Eddington limit continuously. Observations show accretion rates vary dramatically over time. Holes go through active phases where they consume material rapidly, then quiet phases where accretion nearly stops. Average rates fall well below the Eddington limit. With lower average rates, growth takes longer. Additionally, not all the consumed mass gets converted to whole mass. Some material gets expelled in jets and winds before crossing the event horizon. The fraction lost depends on magnetic field strength, disk properties, and rotation rate. For typical values, perhaps half the available mass escapes. This further slows growth. Mergers help but also have limitations. When galaxies collide, their central holes eventually merge. The merged hole weighs roughly the sum of the parent holes. Repeated mergers can build massive holes over time. However, mergers require galaxies to find each other. Galaxy collision rates are finite. Only so many mergers can occur in 10 billion years. Computer simulations model hole growth, including both accretion and mergers. The simulations start with seed holes in the early universe and evolve them forward using realistic accretion rates and merger probabilities. Most simulations struggle to produce holes as massive as Messier 87's within the available time unless they assume very high accretion rates or frequent mergers. This suggests we are missing something. One possibility is that seed holes were more massive than expected. Instead of forming from stellar collapse at 100 solar masses, maybe they formed through direct collapse of gas clouds at 10,000 or 100,000 solar masses. Starting with heavier seeds reduces the required growth factor. Another possibility involves dark matter. Dark matter particles could be captured by the hole's gravity and consumed, adding mass. If dark matter concentrates near galactic centers, this could significantly boost growth rates. However, dark matter's properties remain poorly understood, making this scenario hard to test. A third option suggests the Eddington limit gets violated. Under certain conditions, holes might accrete faster than the limit predicts. If accretion happens in thick disks or through chaotic flows, radiation pressure might not halt infall as efficiently. Super Eddington accretion could allow rapid growth. Evidence for this comes from observations of very distant holes. These objects existed when the universe was less than 1 billion years old. Some already weighed billions of solar masses. The short time frame makes standard growth mechanisms insufficient. Super Eddington accretion, or massive seeds, seem necessary. Messier 87 is not the most massive hole known. The record holder weighs 66 billion solar masses, 10 times heavier. That object sits in a galaxy billions of light years away. Its mass pushes theoretical limits even harder. Explaining such extreme masses remains an active area of research. Mass measurements also reveal correlations with galaxy properties. Heavier holes sit in more massive galaxies. The hole-to-galaxy mass ratio stays remarkably constant, around 0.1%. This suggests a connection between hole growth and galaxy growth. Understanding that connection is key to understanding both. The correlation implies that holes and galaxies evolve together, influencing each other through processes that reach across thousands of light years. Cosmic holes spin. They must. Every object that forms from rotating material inherits that rotation. Stars rotate, planets rotate, galaxies rotate. Holes formed from such material rotate as well. The question is how fast. There is a maximum rotation rate. The limit comes from relativity. As a hole spins faster, frame dragging becomes stronger. Space near the hole gets pulled along, rotating with it. At maximum spin, space at the horizon rotates at light speed. Pushing beyond that would require exceeding light speed, which physics forbids. Messier 87 spins close to this maximum. Measurements of the accretion disk's inner edge suggest a spin parameter around 0.9. The spin parameter ranges from 0 for a non-rotating hole to 1 for maximum spin. 0.9 means the hole rotates at 90% of the theoretical maximum. At that rotation rate, the hole completes one revolution every few hours. That sounds slow until you consider the scale. The horizon has a 19 billion mile diameter. Material at the equator travels that entire circumference in hours. The velocity approaches a significant fraction of light speed, even though the rotation period seems long. High spin has dramatic consequences for the surrounding environment. Frame dragging extends the ergosphere farther from the horizon. Material can orbit closer before falling in. The innermost stable orbit sits almost at the horizon itself for a maximally spinning hole. This allows the accretion disk to extend deeper into the gravitational well, reaching regions where gravity is stronger and orbits are faster. Faster orbits mean more energy release. The efficiency of converting rest mass to radiation increases with spin. A non-rotating hole converts about 6% of infalling mass to energy. A maximally spinning hole converts 42%. This seven-fold increase makes spinning holes far brighter than non-spinning ones at equivalent accretion rates. The extra efficiency comes from deeper gravitational wells. Particles orbiting close to the horizon lose more orbital energy per unit time than particles farther out. That energy gets radiated away. More energy radiated means brighter emission. The disk around a spinning hole shines brighter in its inner regions, producing a distinct spectral signature. Observers use that signature to measure spin. By analyzing the shape of emission lines from iron atoms in the disk, astronomers determine how close the emitting gas orbits. Iron lines get distorted by gravitational redshift, Doppler shifting, and relativistic beaming. The combined effects produce a characteristic broadened and skewed line profile. Fitting that profile with models gives the spin parameter. For Messier 87, the iron line fits require a spin parameter above 0.8. Combined with other measurements, the best estimate is 0.9. The uncertainty is about 10%. Future observations with more sensitive instruments will refine the value. Why does the hole spin so fast? One explanation is coherent accretion. If gas falls into the hole mostly from one direction, angular momentum adds up consistently. Over billions of years, this builds high spin. Random accretion from all directions would average to lower spin. Evidence suggests Messier 87's accretion has been coherent. The hole's spin axis aligns with the galaxy's rotation axis. This alignment indicates that gas feeding the hole comes primarily from the galaxy's disk, where material rotates in a consistent direction. Mergers could disrupt this alignment, but apparently have not significantly. Mergers can also increase spin if the holes orbit prograde before merging. Prograde means the orbital motion matches the parent hole's rotation. Such mergers add angular momentum efficiently. Retrograde mergers, where orbital motion opposes rotation, subtract angular momentum. The final spin depends on the mass ratio and orbital configuration. Simulations show that typical merger scenarios produce moderate spins around 0.7. Reaching 0.9 requires special conditions, multiple prograde mergers, or prolonged coherent accretion. Messier 87's high spin suggests it experienced favorable growth conditions throughout its history. The spin also affects gravitational waves. When two spinning holes merge, the final hole's spin depends on how the parent spins aligned. Aligned spins add. Anti-aligned spins partially cancel. The gravitational wave signal encodes this information. Detectors like LIGO measure spin from wave properties. Most detected mergers produce final spins between 0.6 and 0.8. This matches expectations from theoretical models. Observing a very high spin hole like Messier 87 through gravitational waves would require detecting the final moments of a carefully aligned merger. Future space-based detectors might achieve this. High spin creates another interesting effect: superradiance. Certain waves traveling near the ergosphere can extract rotational energy from the hole. The wave reflects off the curvature, gaining energy in the process. The hole slows slightly. This phenomenon, predicted in the 1970s, has never been directly observed but should occur if the physics is correct. Detecting superradiance would require extremely sensitive instruments. The effect is subtle, producing small changes in the hole's rotation over long periods. Currently, we cannot measure hole spins precisely enough to detect such changes. Future observatories may have sufficient sensitivity. Spin also determines how much energy can be extracted before the hole spins down completely, a process that becomes important when considering the hole's ultimate fate. The event horizon marks the boundary between escape and imprisonment. Cross it and you never come back. Not even light can return from beyond that line. It is the ultimate point of no return. For Messier 87, that boundary stretches 19 billion miles across. The size depends entirely on mass. Heavier holes have larger horizons. The relationship is linear. Double the mass and you double the horizon diameter. This simplicity makes horizons easy to calculate once you know the mass. But horizons are not physical surfaces. Nothing solid exists at the boundary. No barrier blocks your path. No wall stops your descent. The horizon is purely a mathematical construct, the radius where escape velocity equals light speed. Below that radius, escape becomes impossible because it would require faster than light travel. An observer falling toward the horizon would notice nothing special at the crossing point. From their perspective, space appears smooth and continuous. They cross the boundary in finite time, perhaps seconds or minutes depending on the hole's mass. The transition is unremarkable. They would not realize they had crossed until it was too late. From outside, the situation looks completely different. A distant observer watching someone fall sees them slow down as they approach the horizon. Time dilation causes their clock to tick slower and slower. Light from their body redshifts, dimming and reddening. Eventually, they appear frozen just above the boundary, their light stretched to infinite wavelength. They never actually cross from the outside observer's perspective. This apparent paradox confuses many people. Does the person cross or not? The answer is both. From the faller's frame, they cross in finite proper time. From the external frame, the crossing takes infinite coordinate time. Both descriptions are valid within their respective reference frames. The horizon's size also relates to temperature. Stephen Hawking discovered that cosmic holes radiate thermal energy, a process now called Hawking radiation. The temperature depends inversely on mass. Larger holes are colder, smaller holes are hotter. For Messier 87, the temperature is incredibly low, around 1/10 billionth of a degree above absolute zero. At that temperature, the hole radiates negligibly. The Hawking radiation output is far less than the cosmic microwave background radiation the hole absorbs. The hole actually gains mass slightly from absorbing background photons faster than it radiates. This situation will persist until the universe expands and cools enough that background radiation drops below the Hawking temperature. That will not happen for trillions of years. Eventually, though, the universe will expand and cool. Background radiation will fade. The hole will begin losing mass slowly through Hawking radiation. The process accelerates as the hole shrinks because temperature increases when mass decreases. Smaller holes radiate faster. The final stages happen explosively. When the hole shrinks to mountain mass, it radiates at tremendous power. The temperature soars, particles stream away. Within seconds, the remaining mass evaporates in a burst of gamma rays. The hole disappears completely, leaving nothing behind. For a hole like Messier 87, evaporation takes 10 to the 100 years. That is a 1 followed by 100 zeros. For comparison, the current age of the universe is about 10 to the 10th years, a 1 followed by 10 zeros. Hole evaporation happens on timescales incomprehensibly longer than the universe's current age. The horizon also has interesting geometric properties. In curved spacetime, defining a surface's area requires careful mathematics. For a non-rotating hole, the horizon is spherical. Its area equals 4 times pi times the radius squared, just like a normal sphere. Rotation changes the geometry. A spinning hole's horizon is an oblate spheroid, flattened at the poles and bulging at the equator. The flattening depends on spin. Faster spin means more flattening. At maximum spin, the polar radius is half the equatorial radius. The area formula becomes more complicated, involving elliptic integrals. Despite the shape change, the horizon still has a well-defined area. Black hole thermodynamics tells us that horizon area relates to entropy. Entropy measures disorder or information content. The relationship says a hole's entropy equals its horizon area divided by 4 times the Planck area. This connects gravity to quantum mechanics in a deep way. The formula implies that information about infalling matter gets encoded on the horizon surface. This idea leads to the holographic principle, which suggests that all information in a volume of space can be described by data on the boundary of that volume. The principle has broad implications for theoretical physics, suggesting that 3-dimensional reality might emerge from 2-dimensional information. These concepts remain theoretical. We cannot test them directly because we cannot probe near the horizon of an actual cosmic hole. The nearest hole is thousands of light years away. The journey would take millions of years at current spacecraft speeds. Even if we could reach it, the tidal forces would destroy any probe long before it approached the horizon. Tidal forces are the real danger, and they become important well before you reach the horizon itself. Stars orbit the galaxy's center in elliptical paths. Most maintain safe distances, never coming close to the central hole. Occasionally, a star's orbit takes it too near. When that happens, gravity destroys it. The process is called tidal disruption. It begins when the hole's gravitational force on the star's near side exceeds the force on its far side by enough to overcome the star's self-gravity. This threshold occurs at a specific distance called the tidal radius. For a star like our own approaching Messier 87, the tidal radius sits about 100 million miles from the hole's center. At that distance, the star begins to stretch. The near side experiences stronger gravity than the far side. The difference pulls the star into an elongated shape. As the star continues falling, the stretching intensifies. Material on the near side accelerates toward the hole, while material on the far side lags behind. The star transforms from a sphere into a long filament of gas. Eventually, the star rips apart completely. Gas from the near side spirals into the hole within hours or days. Gas from the far side escapes into space, never to return. About half the star's mass gets consumed. The other half disperses. The destruction happens violently. releasing enormous energy. The energy comes from the gas heating up as it falls. As stellar debris spirals inward, it collides with itself and with existing material in the accretion disk. Collisions convert kinetic energy to heat. Temperatures rise to millions of degrees. The hot gas radiates across the electromagnetic spectrum, producing a bright flare visible from Earth. Astronomers have observed dozens of these tidal disruption events. They appear as sudden increases in galaxy brightness, rising over weeks and fading over months. The light curves and spectra match predictions from tidal disruption models. Each event provides information about the hole's mass, spin, and accretion properties. One well-studied event occurred in 2011. A telescope surveying for supernovae detected a bright flare in a galaxy 2.8 billion light-years away. Follow-up observations showed the spectrum contained lines from helium and hydrogen, consistent with stellar material. The brightness peaked at 1 trillion times our home star's luminosity before fading over several months. Analysis indicated a hole weighing about 3 million solar masses had destroyed a star slightly larger than our own. The star's final moments played out predictably. Its orbit brought it too close. Gravity stretched it beyond recovery. The near side crossed the event horizon first, disappearing forever. The far side escaped, carrying half the star's mass into interstellar space. The middle section formed an accretion flow, spiraling inward over weeks. Tidal disruption events are relatively rare. A typical galaxy experiences one every 10,000 to 100,000 years. The rarity comes from geometry. Most stellar orbits never pass close enough for disruption. Only stars on highly eccentric paths or stars scattered by gravitational interactions reach the tidal radius. Near Messier 87, the rate might be higher because the galaxy is so massive. More stars means more chances for close encounters. Additionally, the galaxy's core is dense, with stars packed closer together than in typical galaxies. Close packing increases the likelihood of gravitational interactions that perturb orbits, sending stars toward the hole. Observing a tidal disruption event near Messier 87 would provide valuable data. Scientists could measure the hole's mass independently by analyzing the flare properties. They could determine the star's composition from the emission spectrum. They could track how the disrupted material settles into the accretion disk. All this would improve understanding of accretion physics. So far, no disruption event has been detected at Messier 87. The galaxy is constantly monitored by telescopes searching for transient events. Automated surveys compare images taken days or weeks apart, looking for brightness changes. When a flare appears, rapid follow-up observations capture the event's evolution. Future surveys will increase detection rates. Next-generation telescopes will survey larger areas of sky more frequently. They will detect fainter flares at greater distances. Machine learning algorithms will identify candidates in real time, triggering immediate follow-up. The combination will reveal hundreds or thousands of tidal disruption events per year. Each event illuminates the region around the horizon, revealing details about gravity's most extreme effects and how matter behaves under impossible conditions. Tidal forces arise whenever gravity varies across an object. The side facing the source feels stronger pull than the opposite side. For small objects near weak gravity sources, the difference is negligible. Near a cosmic hole, the difference becomes deadly. Imagine falling feet first toward Messier 87. Initially, nothing seems wrong. Gravity pulls you inward, accelerating you to higher and higher speeds. You fall for weeks, crossing millions of miles. The hole remains ahead, a dark circle blocking stars. Then you notice a strange sensation. Your feet feel heavier than your head. The difference increases as you fall. Soon your feet pull noticeably harder than your head. The sensation becomes painful. Your body stretches, bones strain, muscles tear. The force intensifies relentlessly. Within minutes, the stretching exceeds what your body can endure. You do not survive. Long before reaching the horizon, tidal forces rip you apart. Your body stretches into a thin stream of atoms, a process colorfully called spaghettification. The stream continues falling, now just a ribbon of disconnected particles. They cross the horizon separately, vanishing one by one. The distance where this happens depends on the hole's mass. Larger holes have weaker tidal forces at the horizon. This seems counterintuitive until you realize that tidal force depends on the gravity gradient, not the absolute gravity strength. Gradients decrease with size because the horizon's radius increases faster than surface gravity. For Messier 87, you could actually cross the horizon intact. The tidal force at the horizon is weak enough that a human body survives. You would experience gentle stretching, uncomfortable but not lethal. The real danger comes after crossing. As you fall toward the singularity at the center, tidal forces increase rapidly during the final descent, eventually reaching levels that destroy anything. Smaller holes kill you before you reach the horizon. A stellar mass hole weighing 10 times our home star would spaghettify you thousands of miles above the boundary. You would never experience crossing. Your atoms would cross individually, stripped from your body by forces stronger than any chemical bonds. Planets suffer the same fate as people. A planet wandering too close gets stretched into an ellipsoid, then into a filament, then into a cloud of debris. Rocky planets shatter. The fragments continue orbiting briefly before spiraling inward. Gas giants fare slightly better, their larger size allowing them to maintain cohesion longer, but eventually even they succumb. The tidal radius for a planet is larger than for a star because planets are denser. Density determines how strong self-gravity is. Higher density means stronger self-gravity, which can resist tidal forces longer. A rocky planet might survive closer to the hole than a comparable mass gas cloud. However, ultimately, all objects have a limit beyond which they disintegrate. Tidal forces also affect the accretion disk. Gas in the disk experiences tidal stretching. The effect helps drive turbulence, mixing material and transporting angular momentum. Without tidal forces, disk dynamics would be simpler but less efficient at moving mass inward. The stretching creates shear, which generates heat through friction. Black holes orbiting each other experience mutual tidal forces. Each hole raises a tidal bulge on the other. The bulges lag slightly behind the line connecting the holes because space-time curvature delays their response. This lag creates friction, dissipating orbital energy. The energy loss causes the orbit to decay over time. Eventually, the holes merge. The final moments involve extreme tidal deformation. Each hole's horizon stretches toward the other. They make contact, forming a bridge of connected space-time. The bridge grows, the horizons merge, and a single larger horizon forms. The process takes milliseconds, releasing enormous gravitational wave energy. Simulations show the merged horizon initially has an irregular shape. It ripples and vibrates like a disturbed water droplet. The vibrations radiate gravitational waves, carrying away excess energy. Within seconds, the horizon settles into a smooth oblate spheroid, representing the new hole in equilibrium. The center of that equilibrium is a singularity, a point where space-time curvature becomes infinite and physics breaks down completely. There is a distance from the hole where light does not fall in and does not escape. It simply orbits forever, trapped in an endless loop. This occurs at the photon sphere, a shell of space where gravity bends light paths into perfect circles. For Messier 87, the photon sphere sits about 28 billion miles from the center. Any photon arriving at exactly that distance with the right trajectory will circle the hole indefinitely. The orbit is unstable. The slightest perturbation sends the photon spiraling inward or escaping outward. Nothing can maintain a stable photon orbit for long, yet mathematically, the orbit exists. The existence of photon orbits creates strange optical effects. If you hovered just outside the photon sphere and looked around, you would see multiple images of distant stars. Light from those stars curves around the hole multiple times before reaching your eyes. Some light completes half an orbit, Some completes one full orbit, some completes 2 or 3 orbits. Each path creates a separate image. The images form a series of rings around the whole. The primary ring comes from light that bends around once. A fainter secondary ring comes from light that wraps around twice. Tertiary and higher order rings grow progressively dimmer and closer together. The pattern converges on the photon sphere radius, creating a bright boundary. This boundary is what creates the shadow visible in photographs. Light from the accretion disk travels toward us. Some of it passes safely around the hole, reaching our telescopes. Light passing too close bends into the photon sphere and disappears. The transition region appears as a dark circle surrounded by a bright ring. The ring is not the photon sphere itself, but light from the disk lensed around it. The photon sphere's radius depends on the hole's mass and spin. For a non-rotating hole, the photon sphere sits 3 times farther from the center than the event horizon. Spin changes this ratio. A maximally spinning hole has its photon sphere closer to the horizon, about twice the horizon radius. Messier 87's high spin places its photon sphere relatively close in. Photons orbiting at the photon sphere experience extreme time dilation. Their clocks run slower compared to distant observers. A photon completing one orbit might experience nanoseconds while years pass outside. The effect is purely gravitational, caused by the intense space-time curvature at that radius. Interestingly, massive particles can also orbit near the hole. Material with mass requires rocket thrust to maintain a circular orbit inside the photon sphere. The required thrust increases as you approach the sphere from outside. At the photon sphere itself, infinite thrust would be needed. Below the sphere, no amount of thrust can maintain a circular orbit. This defines the innermost stable circular orbit. For material with angular momentum, this orbit sits farther out than the photon sphere. Depending on spin, the innermost stable orbit ranges from 6 horizon radii for a non-rotating hole to just above the horizon for a maximally spinning one. Material in the accretion disk cannot orbit closer than this limit. At the innermost stable orbit, particles plunge inward. They lose their circular motion and fall straight toward the horizon. The transition happens quickly. One moment the particle orbits normally. The next, it crosses the stability threshold and begins free falling. Nothing can stop the descent. The plunge takes seconds or minutes depending on hole mass. During that time, the particle accelerates to significant fractions of light speed. It experiences intense tidal forces. If the particle is part of a larger structure, that structure gets torn apart. Individual atoms separate, each following its own geodesic path through space-time. The plunging region between the innermost stable orbit and the horizon is called the plunging region. Surprisingly, this region can contribute to observable emission. Particles plunging inward still radiate energy. They collide with each other and with magnetic fields. These interactions produce radiation detectable from outside. Modeling the plunging region accurately requires sophisticated simulations. Recent calculations show the plunging region affects the shadow's appearance. Emission from plunging material adds light near the photon sphere, slightly altering the bright ring's width and brightness distribution. The effect is subtle but measurable with sufficient resolution. Future observations may detect these signatures. The photon sphere also plays a role in gravitational lensing. When a cosmic hole passes between Earth and a distant background object, light from that object bends around the hole. Some light paths take extreme routes, wrapping around multiple times before escaping. These paths create a complex pattern of lensed images. Einstein predicted this effect in the 1930s. He calculated that a perfectly aligned hole would create an Einstein ring, a complete circle of light surrounding the dark shadow. Messier 87's image shows something similar, though the alignment is not perfect and the ring is actually emission from the disk rather than a background source. Photon spheres exist around any spherically symmetric mass distribution. Even Earth has a photon sphere, though it sits deep inside the planet where no light can travel. Neutron stars have photon spheres just above their surfaces. Only around cosmic holes do photon spheres exist in empty space where photons can actually orbit. The photon sphere marks the edge of the observable region. Beyond it lies territory where light cannot escape, where information vanishes, and where our ability to see ends permanently. When material falls into the accretion disk at unusually high rates, the hole responds with violent outbursts. These bursts release more energy in seconds than ordinary stars produce in millions of years. The radiation travels across the universe, arriving at Earth as gamma-ray flares visible to specialized telescopes. Gamma rays are the highest energy photons known. They carry millions or billions of times more energy than visible light. Creating them requires extreme conditions, temperatures of billions of degrees, particles accelerating to near light speeds, or exotic nuclear reactions. The accretion disk around Messier 87 produces all three. The bursts occur irregularly. Sometimes months pass between events. Sometimes multiple bursts happen within days. The unpredictability makes them challenging to study. Telescopes must watch continuously, ready to capture data when a burst appears. Missing an event means losing information that might not repeat. One particularly bright burst occurred in 2008. Gamma-ray telescopes detected a sudden increase in emission from Messier 87. The brightness rose by a factor of 3 within 6 hours, peaked, then declined over several days. Follow-up observations at other wavelengths showed corresponding increases in X-ray and optical emission. Analysis revealed the burst originated from the jet. Material accelerating along magnetic field lines had encountered a shock wave, a region where fast-moving plasma crashes into slower material. The collision energized particles to extreme velocities. Those particles then radiated their energy as gamma rays through synchrotron and inverse Compton processes. Synchrotron radiation happens when electrons spiral around magnetic fields. The spiraling acceleration causes the electrons to radiate. Higher electron energies produce higher frequency photons. In the gamma-ray regime, this requires electrons moving at 99.99% of light speed. Only the most extreme environments can accelerate particles to such velocities. Inverse Compton scattering boosts photon energies. Low-energy photons collide with high-energy electrons. The collision transfers energy from the electrons to the photons, converting radio or optical photons into X-rays or gamma rays. The process is efficient in regions with both strong radiation fields and fast electrons. Both mechanisms operate in the jet simultaneously. Synchrotron radiation creates the initial photon field. Inverse Compton scattering boosts those photons to higher energies. The combination produces a broad spectrum spanning radio waves through gamma rays. Observing across this entire range reveals the physical conditions in the emitting region. The gamma-ray emission varies on timescales of hours. This short variability constrains the size of the emitting region. Light travel time limits how quickly an extended region can change brightness coherently. If emission comes from a region 1 light hour across, brightness cannot change faster than 1 hour. Measuring variability timescales therefore measures region sizes. For Messier 87, hour-scale variability implies emission regions roughly 1 light-hour in size. That is about 1 billion kilometers, comparable to the distance from our home star to Jupiter. This tiny region produces radiation detectable across billions of light-years. The energy density must be extraordinary. Calculations show magnetic field strengths reaching thousands of Gauss, temperatures exceeding 1 trillion degrees. These conditions rival the most extreme environments in the universe. Only cosmic hole jets, neutron star mergers, and certain supernovae reach comparable extremes. The fact that Messier 87 maintains such conditions quasi-continuously demonstrates the phenomenal power output of an actively feeding hole. The bursts also carry information about the jet's structure. Different burst patterns suggest different triggering mechanisms. Some bursts correlate with changes in accretion rate. Others seem to result from internal jet instabilities. Distinguishing between scenarios requires combining observations across multiple wavelengths and modeling the underlying physics. Recent work focuses on the jet's magnetic structure. Observations suggest the magnetic field has a helical configuration, spiraling along the jet axis. This geometry arises naturally when a rotating disk launches material along field lines. The helical structure helps confine the jet and might explain why jets remain collimated across such vast distances. Polarization measurements support this picture. Polarized light has its electric field oscillating in a preferred direction. Synchrotron radiation is naturally polarized, with the direction determined by magnetic field orientation. Measuring polarization across the jet reveals the field geometry. Results show systematic patterns consistent with helical fields. The discovery of gamma-ray bursts from Messier 87 places it in a special category. Most cosmic holes do not produce detectable gamma rays. Either their jets are too weak, pointed away from Earth, or the emitting region is too faint. Messier 87's proximity and favorable orientation make it one of the best targets for studying jet physics. Understanding these bursts helps answer fundamental questions about how holes convert gravitational energy into radiation, but the total power output still dwarfs anything else in the galaxy. Earth's magnetic field measures about half a Gauss at the surface. It is strong enough to deflect compass needles and protect the planet from solar wind. Near the accretion disk around Messier 87, magnetic fields exceed 10,000 Gauss, 20,000 times stronger. These fields control everything that happens in the disk. They regulate how material spirals inward. They launch jets from the poles. They determine which particles get accelerated and which get absorbed. Without magnetic fields, the disk would behave completely differently. Accretion would slow, jets would disappear, the hole would grow dark. The fields originate from the disk's motion. Electrically charged plasma moving through space generates currents. Currents create magnetic fields. As the disk rotates, it acts like a dynamo, amplifying weak seed fields into powerful structures. The process is self-sustaining. Stronger fields affect plasma motion, which generates even stronger fields. This dynamo process has limits. Eventually, magnetic pressure becomes comparable to gas pressure. At that point, fields cannot strengthen further without disrupting the disk. The equilibrium state has magnetic and gas pressures roughly equal, a condition called equipartition. Observations of Messier 87 suggest the disk operates near equipartition. The field geometry is complex. Instead of simple dipoles like Earth's field, the disk contains tangled loops and twisted flux tubes. These structures constantly evolve, reconnecting and rearranging. When field lines reconnect, they release stored magnetic energy explosively, accelerating particles and heating plasma. Magnetic reconnection happens throughout the disk. Small-scale reconnection events occur constantly, contributing to the overall heating. Larger events produce flares, sudden increases in brightness caused by massive energy releases. These flares can outshine the steady disk emission temporarily, then fade as the reconnected fields relax. The strongest fields concentrate near the poles. Here, magnetic flux from the entire disk converges, creating channels through which jets escape. Field strengths in these channels can exceed 100,000 Gauss. The fields are so strong that they dominate the dynamics completely. Particles cannot cross field lines, they can only move along them. This confinement is what creates jets. Particles near the poles get funneled along field lines pointing away from the disk. They accelerate as they follow the lines outward. The magnetic pressure pushes them to higher and higher speeds. By the time they leave the immediate vicinity of the hole, they are moving at 99% of light speed. The acceleration mechanism involves frame dragging. Rotating space-time drags magnetic field lines around like a spinning conductor drags magnetic flux. The dragging twists the fields, creating tension. The tension releases by flinging particles outward. This process, called the Blandford-Znajek mechanism, extracts rotational energy from the hole itself. The Blandford-Znajek mechanism only works around spinning holes. Non-rotating holes cannot drag space-time. Without dragging, no twisting occurs. Without twisting, no jets form. This explains why the most powerful jets always come from rapidly spinning holes like Messier 87. Measuring magnetic field strengths directly is challenging. We cannot send probes to measure them locally. Instead, astronomers infer field strengths from emission properties. Synchrotron radiation intensity depends on both particle density and magnetic field strength. By measuring radiation and estimating density, field strength can be calculated. Polarization provides another diagnostic. Synchrotron emission from ordered magnetic fields is highly polarized. Random fields produce unpolarized emission. By measuring polarization fraction and direction, astronomers map the field structure. Observations of Messier 87 show polarization patterns consistent with ordered fields threading through the disk and jet. Recent observations with the Event Horizon Telescope included polarization measurements. The results revealed field lines looping through the accretion disk, concentrated near the inner edge. The pattern matched predictions from simulations. The agreement confirmed that models of magnetic field generation and dynamics are basically correct. The fields also affect what happens to infalling material. Charged particles spiral around field lines, unable to cross them. This restricts how they can move. Particles can drift along fields or slowly diffuse across them, but rapid cross-field motion is forbidden. The restriction creates anisotropic flows, where motion parallel to fields differs from motion perpendicular to them. Anisotropic flows complicate the physics. Standard hydrodynamics assumes fluid motion is isotropic, the same in all directions. Magnetized plasmas violate this assumption. Describing their behavior requires magnetohydrodynamics, a more complex framework. Simulating magnetized disks demands enormous computational resources. Despite the difficulty, simulations reproduce observed features. They predict jet formation, disk temperatures, emission spectra, and variability patterns. The success validates our understanding of magnetic field physics in extreme environments. It also provides a foundation for interpreting observations of more distant or fainter holes. The magnetic fields also connect to one of the deepest mysteries: how these holes grew so enormous so quickly, faster than conventional theories allow. 6.5 billion solar masses. That number is the problem. Conventional growth models cannot produce something this massive within the time available. The universe is 13.8 billion years old. Messier 87's galaxy formed about 10 billion years ago. That gives 10 billion years for the whole to grow from seed size to its current mass. The math does not work. Start with a seed hole weighing 100 solar masses, a typical mass for holes formed from stellar collapse. Assume it accretes at the maximum rate allowed by physics, the Eddington limit. At that rate, doubling time is roughly 50 million years. 10 billion years allows about 200 doublings. 200 doublings produces a final mass around 10 to the 60 solar masses. That is vastly larger than observed. So where is the problem? The issue is that holes do not continuously accrete at the Eddington limit. Real accretion rates vary. Sometimes holes feed rapidly. Sometimes they barely consume anything. The average rate falls well below the theoretical maximum. Additionally, not all accreted material adds to the hole's mass. Some gets expelled in jets and winds before crossing the horizon. Depending on conditions, anywhere from 10 to 90% of infalling material might escape. The fraction depends on magnetic field strength, disk temperature, and rotation rate. Lower efficiency means slower growth. Even accounting for these factors, reaching billions of solar masses seems difficult. Simulations starting with stellar mass seeds and evolving them using realistic accretion rates typically produce holes weighing millions of solar masses after 10 billion years, not billions. Something is missing from the models. One possibility is that seed holes were much more massive than 100 solar masses. Instead of forming from stellar collapse, maybe they formed through direct collapse of massive gas clouds in the early universe. Such collapses could produce holes weighing 10,000 to 1 million solar masses immediately. Starting with heavier seeds reduces the required growth factor significantly. Direct collapse requires special conditions. The gas cloud must avoid fragmenting into stars. This happens if the cloud stays hot enough that thermal pressure prevents fragmentation. Heating can come from radiation or from turbulence. In the early universe, intense ultraviolet radiation from the first stars might have provided sufficient heating. Computer simulations show that direct collapse is possible under these conditions. Gas clouds weighing millions of solar masses collapse into holes without forming stars first. The process takes only a few million years, fast enough to seed hole growth early in cosmic history. If Messier 87 started with a million solar mass seed, it would only need to grow by a factor of 6,000. 6,000 is achievable through accretion over 10 billion years. Even with average accretion rates well below the Eddington limit, factors of thousands are reachable. This makes direct collapse an attractive explanation. However, it remains uncertain whether the required conditions actually occurred in nature. Another idea involves super-Eddington accretion. The Eddington limit assumes radiation pressure from infalling material pushes new material away, limiting the accretion rate. But if accretion happens through thick disks or chaotic flows, radiation might not escape efficiently. Trapped radiation cannot exert pressure. Without radiation pressure, accretion can proceed faster. Evidence for super-Eddington accretion comes from observations of extremely distant holes. These objects existed when the universe was less than 1 billion years old. Some already weighed billions of solar masses. The short time frame makes standard accretion insufficient. Super-Eddington growth seems necessary. If it works for early holes, it might also work for Messier 87. Mergers provide another growth pathway. When galaxies collide, their central holes eventually merge. Each merger adds the smaller hole's mass to the larger one. Repeated mergers over billions of years can build massive holes. Simulations show that major mergers are common in the early universe, when galaxies were closer together. Evidence suggests Messier 87 underwent multiple mergers. The galaxy shows signs of past collisions, distorted stellar distributions, tidal tails of stars, satellite galaxies in the process of being absorbed. Each collision likely brought a smaller hole that merged with the central one. Adding up these contributions might account for much of the current mass. A combination of mechanisms probably explains the growth. Start with a massive seed from direct collapse. Add continuous accretion over billions of years, sometimes exceeding the Eddington limit. Include multiple mergers with other holes. The combined effect produces the observed mass within the available time. Testing these ideas requires observations of holes at different cosmic epochs. By measuring hole masses and host galaxy properties across a range of distances, astronomers can track how holes grow over time. Patterns in the data reveal which growth mechanisms dominate at different eras. Recent surveys have begun providing such data. Preliminary results suggest a mix of processes. Direct collapse might explain very massive holes forming early. Mergers dominate during the peak era of galaxy collisions, roughly 8 to 10 billion years ago. Accretion contributes throughout, but becomes less important in the modern universe as gas supplies dwindle. Understanding growth mechanisms connects to a broader pattern linking hole mass to the mass of the host galaxy, a relationship that suggests holes and galaxies evolve together. Messier 87 sits at the center of the Virgo galaxy cluster, the largest concentration of galaxies near our own. The cluster contains over 1,000 galaxies, most much smaller than Messier 87. Over billions of years, the central galaxy has been consuming its neighbors, growing larger with each meal. Galaxy cannibalism is common in clusters. The largest galaxy, sitting at the cluster's gravitational center, attracts smaller galaxies. They spiral inward over hundreds of millions of years, eventually merging with the central giant. The process adds stars, gas, and the smaller galaxy's central hole to the growing monster. Evidence of past cannibalism appears in Messier 87's structure. The galaxy's outer regions contain shells and streamers of stars, remnants of destroyed satellite galaxies. These features form when a smaller galaxy gets tidally disrupted during merger. Stars stripped from the satellite spread out, creating diffuse structures that gradually fade as they mix into the larger galaxy. Astronomers have counted dozens of these tidal features. Each represents a separate merger event, a galaxy consumed sometime in the past billion years. The feature's brightness and extent reveal when the merger happened. Bright, well-defined streams indicate recent mergers. Faint, dispersed structures mark ancient events. The most recent major merger occurred about 1 billion years ago. A galaxy weighing 1/10 of Messier 87's mass collided with it, spiraling inward over millions of years before finally merging. The collision triggered intense star formation and fed gas to the central hole, increasing its accretion rate temporarily. That event might explain Messier 87's current activity. Gas from the merger has not completely settled. It continues spiraling inward, feeding the accretion disk. This maintains the bright jets and high-energy emission we observe today. Once the merger gas is exhausted, activity will decline until the next major merger brings fresh fuel. Smaller mergers happen more frequently. Dwarf galaxies weighing millions or billions of solar masses fall into Messier 87 every few 100 million years. Each adds a small amount of mass and can perturb the disk temporarily. The cumulative effect of many small mergers equals or exceeds the contribution from rare major mergers. When galaxies merge, their central holes also merge eventually. Initially, the two holes orbit each other at large distances, embedded in their respective galaxy cores. Dynamical friction gradually brings them closer. They sink toward the merged galaxy's center over millions of years. Eventually, they form a bound binary system. Binary holes orbit each other, losing energy through gravitational wave emission. The waves carry away orbital energy, causing the holes to spiral closer. As the separation decreases, orbital periods shorten and gravitational wave emission intensifies. The process accelerates, culminating in a final plunge and merger. The merger produces gravitational waves detectable across the universe. For holes like those in Messier 87 and its merger partners, the waves peak at millihertz frequencies. Future space-based detectors will observe these events, providing data about hole masses, spins, and merger dynamics. After merging, the combined hole weighs slightly less than the sum of the parent masses. The difference went into gravitational wave energy. For a typical merger, a few % of the total mass converts to waves. That energy escapes at light speed, leaving a single hole with high spin and a characteristic ring-down signature. The new hole settles into a steady state within seconds. Its mass and spin depend on the parent hole's properties and orbital configuration. If both parents spin in the same direction aligned with the orbital motion, the result spins near the maximum rate. Messier 87's high spin suggests this happened during its formation. Each merger also affects the surrounding galaxy. The gravitational disturbance from two massive holes orbiting each other scatters nearby stars. Some stars gain enough energy to escape the galaxy entirely, becoming intergalactic wanderers. Others fall into closer orbits around the merged hole, potentially getting tidally disrupted later. The holes can also receive a recoil kick during merger. Gravitational wave emission is slightly asymmetric if the holes have unequal masses or spins. The asymmetry imparts momentum to the merged hole, kicking it away from the galaxy center at speeds up to several thousand miles per second. Most kicks are small, displacing the hole by light years. Rare configurations produce kicks strong enough to eject the hole completely. Searches for ejected holes have found a few candidates. These objects appear as active cosmic holes displaced from their host galaxy centers. Confirming ejection requires measuring velocities and ruling out other explanations. The evidence remains inconclusive, but theory strongly predicts ejections should occur occasionally. Messier 87 shows no signs of recoil displacement. The hole sits precisely at the galaxy's center, exactly where it should be. This suggests mergers happened with nearly equal masses or favorable spin configurations that minimized kicks. Alternatively, enough time has passed that the hole has spiraled back to the center after an ancient kick. The galaxy's enormous size and the hole's tremendous mass both result from billions of years of consuming neighbors, a process that continues today as smaller galaxies fall inward. Messier 87 did not form in isolation. Its creation involved the most violent events in cosmic history, galaxy collisions. Billions of years ago, smaller galaxies crashed together, their gravitational interaction pulling them into a chaotic dance. Stars, gas, and dark matter mixed as the galaxies merged. The collision process takes hundreds of millions of years. Initially, two galaxies approach each other, drawn together by mutual gravity. As they near, tidal forces stretch both systems. Long streamers of stars get pulled from the outer regions, creating spectacular tidal tails visible across millions of light years. The galaxies pass through each other on their first encounter. Individual stars rarely collide because space between stars is enormous, but gas clouds do collide. The collision compresses the gas, triggering intense star formation. Billions of new stars ignite within a few million years, making the merger system glow brilliantly in ultraviolet and infrared light. After the first pass, gravity pulls the galaxies back together. They orbit around their common center of mass, gradually losing energy through dynamical friction. Dark matter halos interact gravitationally, transferring momentum and slowing the galaxies down. Each orbit brings them closer. Eventually, they merge completely. The two separate structures combine into a single, larger galaxy. The process destroys spiral patterns. If the original galaxies were spirals, the result is usually an elliptical galaxy, a smooth distribution of stars without spiral arms or a disk. Messier 87 is an elliptical, consistent with a merger origin. During the merger, the central holes from both galaxies sink toward the combined center. Each hole weighs millions or billions of solar masses. They drag their surrounding stellar environments along. The holes orbit each other at distances of light years initially, taking thousands of years per orbit. Gravitational interactions with stars gradually steal energy from the binary. As energy drains away, the holes spiral closer. Their orbital period shortens. Within tens of millions of years, they reach separations of light days or light hours. At this point, gravitational wave emission becomes significant. The waves carry away the remaining orbital energy over millions of years. The final plunge happens suddenly. Once the holes get close enough that gravitational waves dominate energy loss, the inspiral accelerates dramatically. Within days or weeks, the separation shrinks from light minutes to the combined horizon size. They merge in a fraction of a second, releasing enormous energy as gravitational waves. The merged hole weighs slightly less than the sum of parent masses. Typically, 2 to 5% of the total mass converts to gravitational wave energy. For a merger producing a 6 billion solar mass hole, that means 100 to 300 million solar masses became pure energy. The power output during the final second exceeds all the stars in the observable universe combined. Computer simulations recreate these mergers in detail. They solve Einstein's equations numerically, tracking how space-time curves as the holes orbit and merge. The simulations predict gravitational wave signals, final hole mass and spin, and recoil velocities. Comparing predictions to observations tests whether we understand the merger process correctly. Real mergers likely involve more than two galaxies. In dense galaxy clusters, multiple galaxies can interact simultaneously. Three-way or four-way collisions produce even more chaotic dynamics. The final result depends on collision angles, velocities, and mass ratios. Most scenarios still produce a single dominant galaxy containing one central hole. Messier 87 probably formed through multiple mergers. Its enormous mass suggests it consumed dozens of smaller galaxies over billions of years. Each merger added mass and potentially increased spin if the incoming hole orbited prograde. The cumulative effect built the monster we observe today. The merger history left observable traces. Besides tidal streams, we can study the ages of stellar populations. Stars formed during mergers have specific ages and compositions. Mapping these properties reveals when major mergers occurred. For Messier 87, studies find evidence for merger activity throughout the past 10 billion years. Future mergers will make it even larger. The galaxy continues consuming satellites today. Multiple dwarf galaxies orbit within Messier 87's gravitational influence, slowly spiraling inward. Over the next few billion years, they will merge, adding their stars and holes to the central system. The violent history of cosmic collisions explains how holes grow, but also raises questions about why holes correlate so precisely with their host galaxy properties. Billions of years ago, the universe looked different. Galaxies were younger, closer together, and filled with more gas. Cosmic holes fed voraciously, consuming material at rates far exceeding what we see today. The feeding powered quasars, the brightest sustained sources in the universe. Quasars shine with the luminosity of 1 trillion stars. Yet all that light comes from a region smaller than our planetary system. The energy density is staggering. Only accretion onto a cosmic hole can produce such extreme output. As gas spirals inward, friction heats it to millions of degrees. The hot plasma radiates across the electromagnetic spectrum. The first quasars were discovered in the 1960s. Astronomers detected mysterious radio sources that appeared point-like in optical images. Spectroscopy revealed that these points were incredibly distant, billions of light-years away. For them to be visible at such distances, they had to be extraordinarily luminous. The mystery deepened when variability was detected. Quasar brightness changed over days or weeks. Light travel time arguments showed the emitting region could be no larger than light days or light weeks across. Producing stellar-level luminosity from such a small region seemed impossible with any conventional energy source. The solution came when astronomers realized what powers quasars. A cosmic hole weighing billions of solar masses, accreting at near the Eddington limit, produces exactly the observed luminosity and variability. The accretion disk shines brightly in optical and ultraviolet light. The jets produce radio emission. The match between theory and observation was too good to be coincidental. Messier 87 might have been a quasar in the past, when its galaxy was younger and richer in gas. The central hole likely accreted at much higher rates. The disk would have shone brilliantly, outshining the entire galaxy. Jets would have been even more powerful, extending farther into space. Evidence supports this scenario. Very distant galaxies observed through powerful telescopes often show quasar activity. The frequency of quasars peaks at redshifts corresponding to the universe at ages of 2 to 3 billion years. This was the peak era of galaxy formation and cosmic hole growth. By studying quasars at different distances, astronomers reconstruct hole evolution. Distant quasars show us holes as they were billions of years ago. Nearby inactive galaxies like modern Messier 87 show what those holes became after fuel ran out. The progression reveals how feeding rates declined as the universe aged and gas supplies diminished. Quasar emission follows characteristic patterns. The spectrum shows broad emission lines from gas moving at thousands of miles per second. The gas orbits the hole Doppler shifted by its motion. Line widths reveal orbital velocities. Combined with luminosity estimates, this gives whole mass. Thousands of quasar masses have been measured this way. The results show masses ranging from millions to tens of billions of solar masses. The most massive quasars formed earliest, when gas supplies were most abundant. Lighter quasars persisted longer, fed by declining but not exhausted gas reservoirs. Quasars also show jets, similar to those in Messier 87. The jets appear as radio lobes extending millions of light-years. Some quasars have jets pointed nearly toward Earth. Relativistic beaming makes these jets appear incredibly bright, earning them the name blazars. The jet emission dominates the spectrum, sometimes outshining the disk. Understanding quasars required decades of work. The physics involves general relativity, plasma physics, magnetohydrodynamics, and radiative transfer. Each component contributes essential pieces. Only by combining all the physics can we model quasar emission accurately. Modern simulations reproduce quasar properties successfully. They start with a massive hole surrounded by gas. The gas forms a disk through angular momentum conservation. The disk heats through friction and viscosity. Radiation escapes, producing the observed spectrum. Jets form through magnetic processes. The match between simulation and observation validates the models. Quasars affect their environment profoundly. Radiation from the disk ionizes surrounding gas across thousands of light-years. Jets plow through the intergalactic medium, creating shocks and heating. Winds blow gas out of the galaxy, suppressing star formation. The combined effects regulate galaxy growth. This regulation explains why whole mass correlates with galaxy mass. As the whole grows and brightens, its energy output eventually becomes strong enough to halt gas inflow. Star formation stops, whole growth stops. The galaxy and whole reach equilibrium, settling into the mass ratio we observe. This feedback mechanism couples whole and galaxy evolution. The connection runs deeper than simple correlation. Wholes actively control when and where stars form throughout their host galaxies.